Um, I just wanted to quickly do some housekeeping. About 28 students are part of a group. 15 students haven't told us who are their group members, so please do that immediately. Okay. And the other thing I wanted to do towards today's class is we are going to learn two more methods. I am sure you have gone to Canvas and you found that I posted two Excel sheets or two Excel files which have a lot of examples from the times I taught this course previously using various methods. So I just want to make sure you are aware of this. Did you guys see this? Yeah, okay. So when you are practicing, just remember this, in the exam, it will be pencil, paper and calculator, no computer for the exam. So what you should do is, if we learn three methods, practice with any of those methods and use this Excel sheet to check your work. That way you have at least 10 or 20 examples to go by. Okay. So please make use of this. My plan for today is to teach the remaining two methods, Secant method and Newton-Raphson method. That will wrap up this module. On next Tuesday, I was originally thinking about discussing module 3 but not include it for the exam on Thursday. But I'm just going to do examples on Tuesday related to module 2. Okay. We'll pick up module 3 after spring break. Okay. And if you're not already aware, next Thursday is our exam, which includes module 1 statistics, 3 problems, and module 2 algebraic equations, 2 problems. See the mock exam. Any question related to that, like the housekeeping details? Okay, thank you. So about 38 students had submitted their participation exercise by 2:30, which is a great number because we are totally 43. 38 submissions is pretty good. This is going to be the way we are going to do participation. We assign it on a day, and before the next class at 2:30 p.m. it is due, standard. Okay, so that you have at least 2 to 4 days to complete it and upload it. I put it in the email, but I want to say it in words. The downside of not submitting is you are slipping down on the curve. If you just never submitted this, but all your friends did, when we calculate the grades, you will be in the bottom half of the class or maybe bottom third, which will consign you to a B minus or a C grade, which you don't want. So please, let's not turn this into Hunger Games. Let's all do well so that if the class average is high and standard deviation is low, the class average will naturally gravitate higher. Okay, let's not have lower grades. Okay, I want you to earn them. Okay, coming back to bisection method, this is the example I started off last time, and in this particular file, I have here the bisection implemented, and you can see here I started with a different guess between -2 and 0, and in the class we did 0 and 1, right? 0 and pi, 0 and pi. So if I go back here, so if I go back here, this is my implementation of graphical method of this function 1 minus x squared minus equal to sine x, or 1 minus x squared minus sine x equal to 0. I generated data between -5 to +5 and did a plot here. Now, again, just to recap, the way you would solve these type of problems is use the graphical method to make your initial guess. So I can clearly see that it intersects between, or it crosses between -2 and 0. Okay. This is the correct function. One. Is this the function we did? 1 minus x squared minus sine x? Yeah. Yeah. Okay. So we did between -2 and 0. Why did we think it's between? Okay. Maybe this is not the same function. Okay, so I'm going to go back here and write 0 to pi and see what we get as the root. Are you getting this 0.64? Yeah? Sorry? Close enough? Okay, so we'll take this 0.64 as our solution. Please listen, no need to write now. I just want to use this to make some points. Number one, in here, I did 22 iterations. You generally don't need so many iterations. Okay. What you do is you start with the initial guess and you keep iterating until A and B themselves don't differ by much. So if you look here, after about 10 iterations, you are starting to see that the first two decimal points are the same. And over time, over iterations, it becomes that they are literally becoming same. That is 0.6366, 0.6369. So the difference is only the fourth decimal point, which is a good time to stop. And if you are automating this in a computer, you can just tell the computer to stop when the difference falls below a certain value, which we call as a tolerance. For the exam, what I would typically do is tell you how many iterations to do. Do 4 iterations with a starting guess of 0 and 5, either that way, or I would say do as many iterations as needed so that the difference between A and B falls below 10%. A and B don't differ from each other by no more than 10%. Something like a criteria would be given to you for you to stop the problem solving. And if nothing is given, just take it from me, 4 iterations good enough. Because even if you get the final answer right, 90% of the credit is approximately going to be given for the steps and not just for the answer. So if you are a genius, make sure you get your final answer right, because if I have only the final answer on the sheet but no steps, we don't know what went on. Okay. All right. So now we want to take the same problem and we want to learn 2 other techniques. I just want you to remember this number so that we know what the answer is, and we'll try to get the same answer using 2 other techniques. Can we do that? All right. So last lecture we saw bisection method, which is more like a way of searching. You start in a range and you keep zeroing down until you converge to a value. So these are based on making an initial guess where the answer might be and then narrowing that range. Okay. The other way of thinking about this is, let's say you have f of x, you have x. Okay. Let's say the function goes like this. It has a root at x naught. This is the root that we are trying to solve. Okay. So this is f of x. And let's say you make a wild guess. You don't know whether relative to the root, whether your wild guess is over here or over here. Just a guess, any number, it doesn't matter. Okay. So our ultimate goal is to be able to come down or come up, as the case is, towards the root. The ultimate aim is to approach the root. So how do we do that? So let's say, for example, you are over here. Okay. At this point, let's say our initial guess is x1. This is our guess. Okay, this is our guess. If you want to go towards the root, how would you pick your next value? Just intuitively asking you, if you want to go towards the root, how would you pick your next value? You don't know the root of whether the root is to the left or right. You don't know that. But what you can know is this is your function f of x equal to 0. That's given. Okay, this is the equation that is you're trying to solve. With me? You can compute its derivative and write f dash of x can be computed. For the problem that we have taken as an example, if I say f of x, which is 1 minus x squared minus sine x equal to 0. That's the function I want to solve. I can compute its derivative. F dash of x would be minus 2x minus cosine of x. Can I do that? Okay. So I take a wild guess. I can evaluate the function at that while guess, and I can also evaluate the slope at that while guess. With these three pieces of information, how can I think about the next step? So you would want to write you would want to write f of x1, that is the next value, is equal to f of x naught, the guess, right, plus the slope times x1 minus x naught. Can I write this? What's wrong with writing with this, or what's correct about writing this? We saw Taylor series in your prerequisite quiz, right? What is Taylor series? If you have a point, let's say this is x, and you consider a neighboring point, we'll call it x plus h. Okay, at x, the value of the function y is y of x. At x plus h, the value of the function is y of x plus h. Taylor series is nothing like it's saying y of x plus h equal to y of x plus h times the slope plus h squared over 2 factorial times the curvature plus the third derivative plus the fourth derivative and so on. That's what Taylor series is. It's a series of higher order corrections so that you can obtain because between these 2 points, you don't know whether the curve goes like this or the curve goes like this. You don't know that. You're saying that if I take my h close enough, I can get away with a linear approximation. That's what Taylor series is. So we are invoking Taylor series to write the value of the function at the next point is equal to the value of the function at the current point multiplied by the slope at the current point. So this is slope at x naught multiplied by distance between the next and current well. Are you with me so far in the story? Yeah, good, good. Okay. First time I'm seeing you smile. That's good. Yeah. Come again. Okay, did I use x1? Okay, sorry. So let's say we'll say x1, and we want to know what is next, x2. Okay, like x2, x1. Okay, so what is slope at x naught? Sorry, slope at x1, that is the f dash of x equal to x1. Slope is nothing but derivative evaluated at that point. We know this from basic calculus, right? Yes. Is there a question? Okay, with me so far. Now you tell me, how should I pick my next value such that I go towards my root? If by some lottery, if my next pick turns out to be the root, what will be the value of f of x2? Louder, please. 0. If x2 happens to be the root, which is the goal, f of x2 is expected to be 0. Would you agree? Yeah, no? Am I the only one who is getting thrilled by this? Okay, so I'll write it in words. If x2 is indeed the root, then f of x2 should be equal to 0, must be equal to 0. At least that's the goal. That's the goal. Yeah, question? Okay. So if f of x2 is to be 0, then I can write 0 is equal to f of x1 plus dy by dx or f dash of x1 times x2 minus x1. Can you rearrange and solve for x2? Can you please do that? Okay, those who are taking pictures, if you write it down, it will register in your mind. It's just psychology. Writing makes you absorb than taking a picture or having a picture. Please write. So x2 is x1 minus f of x1 divided by f dash of x1. That is, you pick the wild guess, and now you have a way to predict what should be your next value that takes you towards the root from any direction. Okay. See. Okay. Good. Okay. Yes.
Would this mean that x2 is equal to x0?
No, this would not be. This would not necessarily mean that your next step will be the root, but it is a way to do this iteratively. I'm going to say that. Okay. So I'm going to erase this. Erase this. X2 equal to x1 minus f of x divided by f dash of x1. F of x1 divided by f dash of x1. So x2, the next value is calculated as a correction to x1, the previous value. So let's say you are here. This correction takes you to, let's say, over here. This is x1, this is x2. X2 also is not going to directly satisfy the equation, but there is nothing that prevents you from applying this again and then calculate an x3 and x4 and x5 and something that eventually takes you to the root, so that when you reach the root, this function will become 0. If this becomes 0, the correction term naturally dies out, leaving you with a converged value. Okay, so instead of using 2 and 1, I'm going to write x next equal to x current minus f of x current divided by f dash of x current. Of course, as with many things in math and physics, the dude Newton put his name on it. So this is Newton-Raphson method. I don't know who's Raphson. Some nobody whose name only appears with this method, probably. Okay, so now you are going to solve this problem using Newton-Raphson method. Okay, so we have this f of x and f dash of x. What was our answer again? We know what the answer is, right? What the root is? 0.6366
X7.
6367. That's our answer. So it's very cool that you can go in knowing the answer. You apply this to figure out how to iterate. So that I'll set up a table and you'll fill it. So we'll have, let's say, iteration number. We'll have x, and we'll call it xi. We'll have f of xi. We'll have f dash of xi. So iteration number 1, that is the initial guess. And we'll guess 0. Okay, that's easy to guess. So you are going to calculate what the second iteration value will be. So f of x equal to 1 minus x squared minus sin x. F of x is 1 minus x squared minus sin x. So f dash of x equal to minus 2x minus cosine x, where x is in radians. Don't forget that. So please complete 4 iterations and see where we are headed. I need to fill my water. Okay, do we have the second iteration? Yeah. Okay, so the slope, initially I wrote the Taylor series. So Taylor series is essentially saying if you are at a point and if you want to predict what the value of the function at a neighborhood or a neighboring point is, you add a correction for the slope, you add a correction for the curvature, third derivative, fourth derivative, and so on. But if the point is close enough, you can get away with only the slope correction, which is where this equation starts. Okay. I can explain this maybe like for now, if you use this formula, I'll be able to explain the Taylor series thing again, maybe since we anyway have a meeting, I can go over that with you. Okay. Okay. But this equation involves the value of the function and the derivative of the function. So you get the those two functions calculated and use them to fill out the table. So yeah, our first guess is 0. Okay, let's do this. Okay. So what is the value of the function at 0? What is the value of the function at 0? That is 1. What is the value of the derivative at 0? Negative 1. Madison, are you okay with this? Value of the function and value of the derivative at 0, evaluated at 0. Okay. So then, when we want to calculate what is the second iteration, that will be the first iteration, which is 0 minus what is the value of the function? 1. What's the value of the derivative? Minus 1. So that gets us 1. So the next iteration value is 1. So once you have this value updated, which is based on these these three numbers. These three numbers. Now you calculate again the function and the slope at that point and calculate the next iteration and keep doing this. Yes.
So like if we're on any given random problem, we should probably start by writing out the function, writing out the derivative of the function, and for x of 0, it can be anything. Like
it can be anything.
5 or 12. Or
anything. The method will converge. It's a matter of iteration. So if you are good at picking the guess correctly closer to your final answer, you will get there in fewer iterations. Yes. Only first derivative. Slope, only slope. Okay, so then let's compute x3. Let's compute x3. x3 is x2 minus the value of the function at x2 minus f dash at x2. This is equal to what is x2? 1. What is f of x2? Negative 0.84, 4 decimal points.
0.8415.
8415, thank you. And what's the value of the slope at 1? At 1?
2.54.
Negative 2.5403.
Yeah.
Okay, 03. Thank you. So I have 1 minus 0.8415 divided by negative 2.5403. So you update this. So you're going to get 1 minus this number, which is of course a number less than 1. Okay, I don't have it worked out with me. Can you tell me what this number is? Okay,
0.66874.
6687. Okay, we'll keep it at 4 decimal points. So the third iteration value is 0.6687. We know our answer is like 63, so we are getting there. We are getting closer. And you need to do this 2 more iterations, you'll probably be there. Okay. So now what's the value of the function?
Negative 0.672.
Negative 0.0672. Is that correct?
Yes.
Okay.
That's slope is negative 2.0780.
2.0780. So I think you have already automated this, right? Good, good. I mean, in the exam, you still have to do this with pencil and paper, but automation will help you understand. Yeah.
That value is negative 2.122.
This one?
That was after.
2.122.
Oh, my bad. Yeah, I'm reaching out.
2.122. What's the fourth to this one? 1. But you get the hang of it. Let's do the next iteration, x4. x4 is going to be x3 minus the function at x3 divided by the slope at x3. So this is 0.6687 minus function is negative 0.0672 divided by the slope being negative 2.1221. So this will again take you closer to the 0.63. Can you tell me? 0.62.
637.
6371. 0.6371. Okay, now take a pause. Take a break. We need to talk about, just like for bisection, we talked about a stopping criterion, which is if A and B get too close, stop the iteration. Here, you don't have 2 guess values, you just have 1 guess value, but they keep going towards the answer as iterations progress. Okay, so let's say this is let's say in general you have xi being the current and xi plus 1 being the next. It could be 1 and 2, 2 and 3, 3 and 4, whatever. Okay. So what you do is you try to check the relative error between xi plus 1 and xi. That is, you define relative error as the absolute value of xi plus 1 minus xi divided by xi as a percentage. Relative change in the value as iterations progress. And if this relative change falls below, I don't know, 10%, 5%, 1%, whatever my chosen criterion is, we stop. So in the exam, I might tell you, iterate until the relative error drops below 5%, or do 4 iterations or something like that. If nothing is given, you can exercise your judgment, do 4 iterations, or pick a relative error of 5% and say I'm now going to stop because it's below 5%. Can you take this home? Like, take it to completion? Yeah, good. Okay. So you're going to do maybe one more iteration until this falls below 5%. Or maybe it has already fallen below 5%. I don't know.
If you do the last iteration, it gets you the same answer.
Below 5%?
I don't know, but it gets you 0.6367.
6367. So we are there by 5 iterations. Maybe Madison, your question will be answered when I talk about secant, how we got there. I'll have another chance to say that. Okay, so I'll take in a couple of minutes. Are we okay? Can I move forward? Right. Okay. So this is the third method, which is first we started with graphical, then bisection, and now we talked about Newton-Raphson. Now, if you think about it, Newton-Raphson, xi plus 1 equal to xi minus f of xi divided by f dash of xi. For some functions, calculating the derivative may not be the easiest thing. We don't want to always calculate derivative, because if it's a simple algebraic function, or like what we had this 1 minus x squared minus sin x. So you can analytically calculate it and you can put it in your computer. But computers can't do this themselves. I mean, they say there are Mathematica or other softwares which can do symbolic computation. But if you look under the hood, they are basically AI models which have rules. They are just mappings. They just work by recognizing pattern. They can't inherently do math. They only mimic a database that has been programmed with or stored in them. Okay. So you have to do this analytically. We don't want that. Why? We don't want to do analytical math. Why? I heard it, but that's not the one I want to know. I want to hear. Why don't we want to do analytical math?
It takes a while.
It takes a while. It is human. It is not good for automation. And we are engineers. We think for efficiency. We don't think for elegance. It's most of the time. Okay.
It becomes increasingly difficult.
It is increasingly more difficult depending on the complexity of the function and number of variables. So we want to repeat the same arguments we made for this in terms of guessing and using the slope to make a local correction and moving towards the root, except this time, instead of using the slope, which is f dash of x, can we do this slightly different? What about what? Lip, you need to give me more details. Right. Okay, good. Now you expand this a little further and tell me the answer. You're almost there. We'll try. Anyone else wants to say something? Okay, so this is what I meant to repeat, to just say how this process works. So let's say you have a function which we are trying to solve. Okay, this is f of x and this is x. So you want to figure out where the root is. That's your problem. Okay, let's say we make a wild guess and the guess is somewhere here. We'll call it x1. We want to go from the guess x1 could also be here. It could be anywhere relative to the root. We want to go from x1 and eventually we want to be able to find the root. Okay, so to do this, I want you to recall something you learned in your calculus courses, which is Taylor series. What is Taylor series? If you have a function at a point x, we'll call it y of x. Okay, and I pick a neighboring point which is at a short distance away. We'll call it x plus h, where h is a short distance. I keep telling short because that is important. And I want to know what will be the value of the function at x plus h. That's the goal. Taylor series allows you to write y of x plus h equal to y of x plus correction for slope plus correction for curvature plus correction for higher order terms. So, I mean, I can just stop here and say, goes with the mathematical derivation, but what does this mean intuitively to correct for slope, curvature, and other terms? Like, can you give me some real world example where we just don't think in terms of slope, but also worry about curvature? Um, you need to give me more detail.
Like, the contours of the bottom.
Okay, okay, a little more.
I mean, like, so that when we're simulating a fluid over air, we need to not just notice up or down, but like how it's curving because the streamline.
Because the streamline is not just a straight line, it's a curve, so you want to account for curvature. I like it, but I'm going to give you a simpler example. Yeah.
What about like when you're making something in a CAD program and you need something to be like a piece to be tangent to a curvature?
I'm not understanding it, but maybe if you tell more, I can
So
understand.
like it'd be like a piece that has a straight line, right? And then another piece that you want to make a relationship to has a curvature, and you need to put them together. So you have one piece that's curved, and a piece that's.
Are you talking about reading maps and globes?
Not exactly. I'm talking about like in a CAD program, making relationships within parts.
So like if I understood right, if you want to project the next point, you are taking the not only the slope but also the curvature to get to the next point. Cool. What I'm about to say was also similar, which is if you want to read the distance between, let's say, Central Avenue and the 385 freeway, you can take a map and put a thread and read the distance. Because why? Over a few miles, the curvature of the earth is not a big deal. It's just slope. But if you want to read the distance between, let's say, Memphis and Chattanooga, it's if you just read the map in a straight line, that doesn't make sense because over that many miles, 400, 450 miles, the curvature of the earth is important. So you would read it off a globe where you would place a thread between the two cities and read the length of the thread, which accounts for not only slope but also curvature. That's exactly what I'm trying to say here. For points that are really close, you don't have to worry about anything else other than slope. But as the distance is increased, you have to worry about higher order terms. Okay, which is where we get the notion that if you write y of x, correction for slope is the slope at x multiplied by h. The correction for curvature is f dashed of x times h squared over 2 factorial, plus and so on up to infinity. Okay, so now we use this part. We use this part to derive Newton-Raphson method. That's what we wrote. Xi plus 1 equal to xi minus f of x divided by f dashed of xi. Now I am asking you to think, if I don't want to evaluate derivatives manually, how can I replace this to kind of get a method which can be automated, which calculates slope, but not with analytical math, but some kind of approximation. How do you approximate slope? That's the question first. If I pick 2 points, x1, x2, forget what the relation between them are. There is f of x1 and f of x2. So we'll pick 2 guesses. And what's the slope here? In very, very crude terms. Change in y divided by change in x, right? Simple. Yeah. That instead of f of x, we are going to approximate f of x in terms of this difference and plug it in here. And that method is called secant method. It's not very different from Newton-Raphson in its core philosophy. It just is a little different in how it treats slope. Okay, so maybe I'll skip a few steps and give you the equation to use, because you got enough philosophy from me. All right. So for Newton-Raphson, we picked a single guess. Okay. For secant method, we are going to pick 2 guesses, x2 and x1. Both are guess values. Yes, yes. You pick 2 guesses. And there is no restriction. The root need not lie between them, nothing like that. You just pick 2 numbers, call them your guesses. Okay. So you want to know what is the third value. That's the goal, right? To iterate towards the goal. The third value would be so we'll call it x1 and x2 are our guesses, and x3 is going to be x2 minus f of x2 divided by f of x1 minus f of x2 multiplied by x2 minus x1. Or sorry, x1 minus x2, the other way. x1 minus x2. And you can change these subscripts and call this next, call this current, and call this whatever you can call it pre-current if you want to. So you have I plus 1, I minus 1. This is next, this is current, this is pre-current. So we already did this problem, f of x equal to 1 minus x squared minus sine x, using graphical. We did using bisection. We also did using Newton-Raphson today. And now for the fourth time, we are going to do this with secant method. Okay. This involves two guesses which contain the root. This involves one guess which can be arbitrarily close or far away from the root. And this involves two guesses, but no constraints. Yeah,
You know where to pick x2.
you can pick anywhere, doesn't matter. That's what I'm saying, no constraint.
So what if I fix my x2 to be ahead of x1? I'm getting further away from what I want.
We can see through examples. The method will gravitate towards the root regardless of where the two guesses are. Okay, we will see it through example. You can we'll pick some good guesses and bad guesses and see in any case you will get the answer. Yeah.
Is the fraction multiplied by the parentheses?
Yeah.
Or is it?
That. Okay, so again, let's set up a table. We'll say iteration number, and we'll say xi minus 1, xi plus 1, and the only things you need are f of xi, f of xi minus 1, f of xi, and then you need to have some kind of a relative error criterion which checks what's the increment difference, that is xi minus 1 divided by xi minus 1 as a percentage. So let's start with iteration 1. Yeah, no, there is no restriction. No restriction. You can,
I
yeah,
could literally pick x1 on this side of the root, and then x2 could be on the other side, and it'll still gravitate towards the root.
I believe so. We'll find out. Okay. So we'll pick xi minus 1 to be 0, and xi will pick something like 0.2. Okay. And now you want to compute what is xi plus 1. So xi plus 1, I being iteration is 1, so x2 is x1 minus minus f of x1 divided by f of x1 minus f of x0 times x1 minus x0. So what is my x1? That would be 0.2 minus, I need to evaluate these two values. What is f of 0? 1. What is f of 0.2? Or maybe those who are trying by programming, I'll give you 2 more minutes to set it up and then I can hope to get answers from you. 0.7613. Thank you. 0.7613. Okay, so I need to plug those in. I need to say f of x1 being 0.7613 divided by 0.7613 minus 1 multiplied by 0.2 minus 0. So to your question, 0.76 divided by a negative number will be positive. It will take you towards the root. And if you take it the other way, that is, if you have the 2 guesses on either side, that is, the root is here, 1 guess is on this side, 1 guess is on the other side, this correction term will bring them together. Where
X minus 1 equals 0, xi minus 1 equals 0.
this is not in the denominator, this is in the numerator.
I was looking at the error though.
Okay, you are asking what happens if my root is really small, it will blow up. That's your question.
The denominator there says xi minus 1, and the xi minus 1 value we have here is 0. So if we divide it by 0, wouldn't that be?
Fair question. There is this will work for cases when you are away from 0, but it won't work really when one of them is 0. So in that case, if your root is 0, let's say your target is 0, then what you do is you just check for the absolute error, which is defined as xi minus 1. If you are targeting 0, this number will get incrementally small. You just have to check for the absolute value. You have to make a small adjustment when to look for relative error and when to look for absolute error. A good question. Okay, can I get this number x2?
0.8378, 0.8379.
8379. Okay, 8379. Everybody is getting 0.8379. Okay. So now when you progress to the next iteration, this value comes over here. Sorry. Yeah, this value comes over here and this value comes over here. So you get 0.2, 0.8379. You initially pick 0 and 0.2. You know the answer to this problem from the beginning, right? That is 0.63 something. The method is kind of shifting itself so that now your interval contains the root. Okay, so that's the advantage. Even bad guesses will quickly correct themselves. Okay, so this is now 0.8379. We need to compute what is x3. X3 is, oh, I have it right here. X3 is x2 minus this. So that would be 0.8379 minus, what is f of x2? That would be 0.78. Yeah, this is x2, this is x1. So this would be Yeah, yeah. Yeah, this is f of 0.2. Now I need f of 0.8379. I need 0.8379. So that is whatever value appears here. I need minus f of 0.8379 divided by f of 0.2 minus f of 0.8379 times 0.8379 minus 0.2. Point 8379 minus 0.2. So I just want to make sure we are going towards the answer and then stop and let you complete it. So if you are doing this on your notebook, all I want for today's participation exercise is a photo of the Newton-Raphson method and this secant method. Upload that to Canvas before 2:30 p.m. next lecture.
This portion completed or just the notes we took?
Complete. Thank you. I would have almost forgotten. Yeah, if you complete it, that would be good, so that you get some fact. Okay. So can I get these values? 0.8379 minus so what were the initial guesses? 0 and 0.2. 0.2 and my function is 1 minus x squared minus sine x, and then my okay, now I have my table. I can do this by myself. What are we getting for x3? After 0.8379, what's the next iteration? Louder, please. 0.6025. So you're saying this is 0.6025?
Oh, no.
Okay. Anyone?
Yeah.
Okay, 0.6025. That's what we are getting. You make sure my program is right.
Oh,
Yeah, you're correct. 0.6025. Okay, 0.6025. So x4 would be 0.6025. See, I'm giving you a trick to easily remember this. Instead of remembering the formula, whatever you have here, okay, minus f of 0.6025 divided by the previous value, which is 8379. So this becomes current and this becomes pre-current. This is f of 0.8379 minus f of 0.6025 divided by 0.6025 minus 0.8379. You have to work out your own way of remembering this. If you write down a formula, you should be able to interpret it in the exam. Okay. This will be 0.6346. So we are getting towards the answer. Okay. So I'm going to show this on Excel shortly. Some of you are very nice and clever. You did it on Excel and posted a screenshot. Totally cool. Please do that. Or do this by hand and send a photo. Either is fine. You can do this by Excel. That's okay. But in the exam, it's paper based. So keep remembering that. Okay. We good? Can I show something on Excel sheet? All right. So this so this, if you look here between rows 10 onwards, okay, hope this is clear. So this is secant method, which I just quickly implemented with Excel. You have to pick your two guesses, and the points I want to make are the choice of the guess should not matter. So I had 0 and 0.2, so it went through the sequence of values that we saw. So let's say I make this minus 10 and plus 10, and we'll generate more iterations. But as iterations go, eventually the method gravitates towards the answer. Okay, most of these methods do. All right. The only difference is, one second, a poor initial guess will only take us more iterations to get there. So it took us at least 12 iterations, which could have been saved if I had taken, let's say, 0 and 1 as my guesses. I can get there in like 5 iterations. Okay. So I'll get it back to 0 and 0.2. Delete all this. So then stopping criteria, how do you stop this thing? So I over here in this column I have what I call as relative error, which is essentially the difference minus 1 or ratio minus 1. Or if you just write, you can easily see that this is the same as what I wrote on the whiteboard. I calculate the relative error, and when that drops below, let's say 0.1%, which I set as my stopping criterion, I don't have to iterate anymore. This answer is already within 0.1%. So it's less than 0.003. I stop. Okay. Same thing about Newton-Raphson. Okay. So I have here the template. I can just copy this and paste it over here, and I have to update the function. So what is my function? 1 minus x squared minus sine of x, and my derivative is minus 2x minus cosine of x. So I gave a guess of 1.5. I got the answer. I can give a guess of 20. I'll still get the answer. Okay, I can give pretty much any guess value, and it will still get me the answer pretty quickly. Not pretty quickly, but sometimes it will take more iterations, but you will get there. Wait, what's happening here? Minus 20. Oh yeah, thank you. So negative 1.4096 is also a root. It kind of gravitates towards the closest root. So I mean, between minus 20 and the root that we were seeking, that is like 0.63 something, there is another root. So we kind of got drawn into that, and we have a root at minus 1.409. Okay. So in a very highly controlled environment like an exam, we would probably tell you the initial guess or tell you where to look for. But in practice, what happens? What are the constraints of reality? Can you talk a little bit about that?
Trying to find the root that you have no way to guess.
There might be multiple routes, and not all of them may be meaningful for the problem you're solving. Like this represents a physical quantity which cannot be negative. So obviously the negative root is not useful for us. So you might always have to pay attention to the physics or the physical constraint. Okay. So that brings us to the last topic. I still have 19 minutes, which is pretty impressive for me because I never keep on time. This is just method, that is tools. We still have to apply it for some mechanical engineering problem. That is the spirit of the course. We don't want to just do math. Okay. So we are going to pick some problems and try to solve them. All right. So if you want to do that, chapter 8. Okay, chapter 8 from the book, which has now shifted to Chapra and Canal, which if you're not aware already. Chapter 8 is essentially the title of the chapter is Case Studies, Roots of Equations. And under that, you want to look for mechanical and aerospace engineering problems, which is basically 8.34 onwards. And I posted this on the syllabus as well as suggested problems. So you want to be able to solve word problems. And let's see if I have the book with me here. Not now. Okay, I'm not able to open the book, but I'm going to read out the problem. Okay. Problem 8.34 from the text, if you have it with you, it's a problem involving pipe flow where you are asked to solve for the friction factor. Okay. I'm going to write out the equation and then you will see why we need a numerical method to solve that problem. We can't solve this directly. So this is problem 8.34 from the textbook, which involves pipe flow. Okay. The friction factor F depends on the Reynolds number Re, okay, and is given by the equation 1 over square root of F equal to 4 times the logarithm with respect to 10 of Reynolds number times square root of F minus 0.4. Solve for F for a Reynolds number of, let's say we'll do a Reynolds number of 10,000. Reynolds number of 10,000, or at least you can now think Reynolds number is a constant whose value we'll pick. But for a given Reynolds number, you need to work out friction factors from this equation. If it were a function that looks like friction factor equal to Reynolds number to the 4 multiplied by some constant, it is not a real challenge. The challenge is this is a nonlinear equation. Not only that, F appears on both sides. So it's not straightforward to solve this because you have to solve this by iteration, or you have to solve this by guessing a value of F and using one of the 4 methods that we learned, like Newton-Raphson or secant or bisection. Okay.
On the test, are you gonna like test? Are you gonna explicitly say use this method or?
If I say use this method, you are expected. If I just give you a word problem and say solve this, you can choose your own method. And I'm going to tell you what are some of the considerations that go into choosing methods. So we learned 4, right? To do the graphing method, you need a calculator or a computer. Okay, usually that is reserved for visualization. The bisection method requires picking an interval where the function changes sign. So you have to keep guessing until you find that interval. So as a method, it's a very unattractive one because finding that guess has a constraint. So if left to the free market, nobody would pick bisection method because bisection method gives you more work than what you need to do. You can pick the other two, Newton-Raphson or Secant. But what's the problem with Newton-Raphson?
Yeah.
We have to take the derivative of this function, which looks not very challenging, but it's still work. I mean, it's not too challenging. It's just square root of f and then logarithm of square root of f. You can still do it. It's still doable. There might be other functions for which it's still more difficult. And then there is secant method for which you can completely automate it and you don't have to do any derivatives. And secant method is by far the most generic method which doesn't have too many constraints. Okay, so you are free to choose any, but how much you understood the relative strength and weakness of these methods will show up in your choice. And which will show up in how much time you spend to solve the problem, which will show up in your eventual score because let's say for these 20 points, you spend half of your exam time, you are left with less time for the other questions. So it's a matter of strategy. Okay. So for this one, right now I'm going to use Newton-Raphson because it doesn't look too bad to me for taking a derivative, and we'll solve it from there. Okay.
Especially for the last one, secant method.
You can visualize this. That is, you can as a function of iteration, you can plot the xi value and watch it go towards the root or watch it converge at the root. So that if you plot this as a function of iteration number, you start at the first iteration with 0.2. What is your answer? 0.63 something, right? 0.6367. That's your answer. As iterations progress, you will watch it kind of go towards that. Okay.
So the reason why we got the other root before was that you were going backwards on that curve.
For each problem, it may visualize differently depending on where the guess is relative to the answer. So sometimes the guess may be here. Let's say your initial guess was 0.9. You will come here like this. Okay. Okay, how do you get started for Newton-Raphson method? Sorry, derivative. So we already have a f, so we want to use a different symbol. So I'm going to call this g of f. G is the label for the function, and f is the independent variable or the variable we are solving for. G of f is defined as 1 over square root of f minus 4 times logarithm of 10 Reynolds number to the power f minus 0.4. This is g of f, which means the derivative g dashed of f would be minus 1/2 f to the 3 by 2 power minus 2 over f or 2 over Reynolds number times f. Am I correct? Logarithm of this means this is, I can write this as I need to differentiate with respect to f. I have 4. This is logarithm of the Reynolds number plus half logarithm of f. This is a constant. So I would have minus 1 over 2f to the 3 halves minus 2 over f. Yeah. Okay. So you would write fi plus 1 equal to fi minus g of f divided by the derivative of g dashed of f, or g of, sorry, I times g dashed of I. Now comes the question, how do I generate a good guess which will get me there sooner? I don't want to get a bad guess and be stuck doing 20 iterations. How to generate a good guess?
Guessing for F.
Guessing for f.
It's bounded on the Moody chart, so
Hmm.
it's easy to know there's relatives in range.
Brilliant. He knows something about the physical situation which he is using to generate the initial guess. And what is the bounding value typically? What I would have done is I will throw away all the ugly parts of the equation and just use the remaining to generate my f. Like I don't like this. This is what makes it transcendental in the first place. I would say 4 log Reynolds number times square root of f equal to 0.4. I would just simplify this to make up an equation which has nothing to do with physics. I just need an initial guess. Okay. So now I would say if Reynolds number is 10 power 4, this is log of Reynolds number times square root of f equals 0.1, which means Reynolds number of square root of f must be equal to so this will be 10 power 0.1, or f is equal to 10 power 0.1 divided by the Reynolds number squared. This is just a way to make up a guess. Okay. My suggestion, like it's not in the book. Throw away all the ugly parts of the equation and you simplify it, linearize it, do what you need to do to get a f. If there is a f power 4 term, just throw it. Yes. It is just a guess because eventually the method will take you towards the answer. You want the order of magnitude right. That's all. If let's say f varies in the order of 0.1, you don't want to pick f is equal to 10 power 6. That will be a disaster. Like you need to do many iterations. But if you got this ordering right, maybe the actual answer is like 0.123134, but you picked 0.09 as your guess, you will get there. Okay. All right. Good. So shall we do this? We have 5 more minutes. So do we have an initial guess? Did you find out the bounds?
So it's bounded, friction factors are bound between 0.01 and 0.1.
They vary between 0.01 and 0.1. Thank you. This is actually the better guess where you take the possible range of values and you pick something out of this. You could say, let's say I pick 0.05 as my guess and start the iteration. So you would have iteration number fi, g of fi, g dashed of fi, and then iteration 1 will pick 0.05. You will have to evaluate g of f and g dashed of f. G dashed. Now, these are all meant for the computer, like automating it so that you have these functions written down and you can quickly fill out this. In the exam, I'll try to make it less painful by asking you limited number of items. Okay. Whether you get there by 4 iterations or not, I'm trying to see how you work out the steps. So I don't care about the final answer too. Just the steps are what I need. You have a question?
Always increases.
Because you're not solving for 0. You're trying to figure out, yeah, for a given Reynolds number, what is the value of f? That is your question. Okay. Okay. We'll continue this in the next lecture. So my plan is on Tuesday, I will just do examples to prepare for the exam. On Thursday, just do examples on module 2, no new concepts. Okay. So please attend. Please do the participation exercise and think about your project problem. After spring break, when you come back, your project description is due. Okay, so keep thinking about it. Thank you.